Welcome again to the tutorials on dynamic system modeling and control. Once again, my name is Hussam Fathi and it's great to have you on this tutorial. This is going to be one of the shortest tutorials in this series of tutorials. It's going to focus on the state space modeling of a simple water tank drainage problem. As I mentioned in the preceding tutorial, this set of tutorials is not going to go into the modeling of the dynamics of fluidic systems in tremendous detail. I'm only going to touch on the subject very quickly through a couple of very simple examples. There's a lot more to the subject than that, and I will be strongly encouraging you to look at specific references for that additional information. But for the purpose of this tutorial, we're just going to be just touching on the basics through a very simple example. The example is the emptying of a water tank. So without further ado, we basically have a tank, and the tank is filled with water, and water is discharging from it through an orifice. And what we would like to do is to model the dynamics of water discharge through this orifice. So the specific goals of this tutorial are, number one, on a high level, to present a simple example of the state space modeling of hydraulic systems, very simple hydraulic systems. And as a more detailed goal, the second goal is to model the dynamics of water discharge from a tank under the influence of gravity. So as we've done before, in order to select the state variables for this system, because it is an energetic system, we can begin by identifying the ways in which the system stores energy and then identifying the corresponding state variables. So the question is, how does this water tank store energy? What are the energy storage modes for this tank? One obvious way that this tank stores energy is potential energy. The water has a certain height in the tank, and to use the nomenclature of fluid mechanics, the water has a certain head, and this head represents the potential energy stored by the water in the tank. From the dynamic systems perspective, that is probably the most important energy storage means that we have to model in modeling the dynamics of this tank as a lumped parameter system. But questions do arise as to whether that is the only energy storage mode. As water flows in the tank, perhaps through the tank and out of the tank, perhaps it accelerates. Perhaps the kinetic energy of the water is something that we need to worry about and perhaps model. There's a question as to whether there are even other ways in which this water stores energy. One may certainly wonder whether the pressure variations in the water represent energy storage, and whether it is important to build a model that captures that. That's an interesting question. And it needs to be answered with a detailed understanding of the dynamics of the fluid in the tank and the importance of modeling those dynamics either in a lumped parameter fashion or in a more detailed fashion. And if we do model the dynamics in a lumped parameter fashion, how many lumps do we need, sort of, to use very vague terminology here? How do we chop up this tank into different pieces for which we build state space models? I'm going to adopt the very simplistic mindset in this tutorial, which is a great starting point for state space modeling of this water tank, that the only energy storage mode that matters for the tank as a whole, as a system, as a lumped parameter system, is storage of potential energy in the form of the water's head. And so that means that I only need one state variable representing this energy stored in the tank, this potential energy stored in the tank. And that state variable is going to be the height of the water in the tank, or the water's head, basically. And so with that in mind, we're now ready to develop a state space model of the system. Because I haven't specified an output, there won't be an output equation. And we only really need one state equation because we only have one state variable. The trick here is to use the law of continuity and to say that the rate of change of the fluid's height with respect to time multiplied by the area of the tank has got to equal the rate at which fluid is discharged from the tank. And if you look into how to model the discharge of fluid from a reservoir through an orifice, if you look at that information from a fluid mechanics textbook, you find that the law of discharge basically says that the discharge rate is equal to some sort of a flow coefficient, K, multiplied by the area of the orifice, A naught, multiplied by the square root of 2 times the gravitational constant, multiplied by the height of the water in the tank, by the head drop across the orifice, basically. And what's important here is to note is that x dot represents the rate of increase of fluid height, and of course discharge decreases fluid height, and so hence we have a negative sign in this state equation. That's really all it takes to build a very simple state space model of discharge from a water tank. Again, I want to emphasize that this tutorial was a very simplistic introduction to just one example, one of the simplest examples of the state space modeling of fluidic systems. And again, I want to emphasize that there are some really great references for further study in this area. As in the previous tutorial, I strongly encourage you to look at William Palm, the textbook System Dynamics by William Palm III, the textbook System Dynamics Modeling, Simulation, Control of Mechatronic Systems by Dean Carnop, Donald Margolis, and Ronald Rosenberg, and the textbook Dynamic Modeling and Control of Engineering Systems by Boyden Kulikowski, John Gardner, and Lowen Shearer. Thank you very much for listening to this tutorial and watching it, and I look forward to the next tutorial with you.